Hi. So we're going to be talking about section 10.1 to 10.3 for chemistry 1151. So this is going to be nuclear chemistry and the last little bit of our course. So just as a quick reminder, you have atomic number, which we use as Z, is the number of protons in the nucleus. Mass number is protons plus neutrons. So remember that was from way back when we first learned this. This is called isotope notation. And it tells us about the different isotopes. Remember, isotopes are things that have the same element but different masses, so same number of neutrons. We put the mass number on the top, the atomic number on the bottom left, and then number of mass number would be protons plus neutrons. So if we wanted to get the number of neutrons, we would take the mass minus the protons to get the neutrons. So that would be mass number minus protons to get neutrons. An isotope are atoms of the same element, but they have different numbers of neutrons, so therefore they have different masses. So we call them by their mass names. For example, carbon-12 has a mass of 12, 6 protons, 6 neutrons. Carbon-13 has a mass of 13, 6 protons, 7 neutrons, and carbon-14 has a mass of 14, 6 protons, 8 neutrons. Notice they all have the same number of protons because they are all still carbon. A radioactive isotope or a radioisotope is unstable and it emits energy and it essentially comes apart until it becomes stable. The radioactivity is that radiation that's emitted as it comes apart. Of all the known isotopes, only 264 stable, but we have another 300 that are naturally occurring but unstable. And then we have pretty much anything man-made or artificial are radioactive, for the most part. There are some that are stable, but not a lot. So if there are three different types of radiation, the first type is going to be alpha radiation, then beta particles or alpha particles, beta particles, positrons, and gamma. Gamma I don't really count as like a radiation. I mean, it is radiation, but it's really easy to do this. So we'll talk about why that one's really easy. So three that you kind of need to know: alpha, beta, and positron. So first start with alpha. Alpha you can write as an alpha sign. This is a Greek lowercase alpha. It is a high energy particle. It's 2 protons and 2 neutrons. So basically it's a helium nucleus and it will have a +2 charge because it only has 2 protons and 2 neutrons. We're not looking at electrons, and so no electrons, um, only nuclei. So we're only looking at the nuclei here. And so there is a particle that is very similar to an electron, a beta particle, but we're only looking at nuclei, so we're not going to think about anything in the top right as far as charge goes here. And then for alpha particles, you can see the symbol alpha. You may also see people write 4-2 in front of it, like in isotope notation, but really it's just a helium nucleus. Beta particle is basically a high energy electron, but it's something that is coming out of the nucleus. And so a beta particle is emitted when a neutron gives up its negativity and becomes a proton. So imagine a neutron kind of has two parts. It has a positive part and a negative part. If it gives away its negative part, now it's just positive. So a neutron turns into a proton. Yes, this happens, and this is going to change, of course, what the element is because we're changing the number of protons. And so nuclear chemistry will actually change what the element is. So for beta particle, we have a mass of 0 because electrons have a mass of 0, and it has a -1 atomic number because it's like the opposite of a proton. So proton would be a 1 positive 1, a -1 would be here. And it has no mass compared to protons. This is true of any electron. We can use the beta, which is a B with like a tail, or you can write E for electron. So a neutron again turns into a proton and gives off a beta particle. So imagine the neutron is just like losing its negativity and becoming fully positive. And notice that the left side and the right side of this equation, like the top and bottom numbers, all add up to equal each other. A positron is the antiparticle of a beta particle. So it's basically like either a proton without mass or a positive electron. And so we will write either beta plus, meaning a positive beta particle, or we'll just write electron, but we'll put a +1 down here. But notice that it still doesn't have mass. So it's not a proton. It does not have mass. This is what happens when a proton gives up its positivity to become a neutron. And this is just because sometimes the ratio of protons and neutrons is off. That's what's making it unstable. And so it will turn protons into neutrons or turn neutrons into protons in order to become more stable. And then gamma rays have it's just high energy radiation. It has no mass and no charge. So sometimes you'll see it written as 0, 0. And then this is the symbol for gamma. It's like a fancy looking Y. It's a Greek letter. So here's a little table for you with the mass numbers, the charges, but you can just remember the symbols, especially the ones that have the numbers in them. So you can write the numbers in front of the Greek letters if you want to as well, if that's helpful. So a nuclear reaction tells us what is the original nucleus, what's the new nucleus, and what kind of radiation did it give off, did it emit? And so emitting would be considered a product because it's going away, it's leaving like a product. The following must be equal on both sides. The top number, the mass numbers, must be equal on both sides, and the bottom numbers, the atomic numbers, must be equal on both sides. This is what I was saying is pretty easy. It's just addition and subtraction. So let's look at an example. So here we have uranium-238, that's the mass number, is turning into an alpha particle, and thorium-234. So we look at the top numbers, 238 equals 4 plus 234. If we look at the bottom, we have 92 equals 2 plus 90. So if I were to block out this one and I would say, okay, what is this over here? Then you would say, well, 4 plus what is equal to 238? Well, that top number must be 234. For the bottom number, we would say 2 plus what equals 92? And we would say the bottom number must be 90. And then you go to look at the periodic table because you know your bottom number, your atomic number tells you the element. And so we would see number 90 is TH or thorium. So we can see our mass numbers and our number of protons or atomic numbers are the same on both sides. So this is one side, and these two have to add up to the left one. So why don't you try this one? What would be the answer here if we had americium-241 giving off an alpha particle or emitting an alpha particle? So pause it and see if you can try. So here we say 241 is equal to 4 plus what? And the answer is 237. The bottom would be 95 equals 2 plus what? And it would be 93. We look at atomic number 93 on the periodic table, find that's neptunium, MP. That's my answer. Don't let it be more complicated than it needs to be. For beta emission, be careful because that bottom number is negative and a lot of people get confused with that. So we have carbon 14 is equal to 0 plus 14. Bottom number 6 is equal to -1 plus, now if I put what here, some people will say like 5 because I say 6 minus 1. But it's 6 equals -1 plus what? Or you can think about it as what minus -1 equals 6. The answer here would be 7. So be very careful when you're doing the beta particle as your radiation because that negative really throws people off. I think switching the order of these around is really helpful. So say 6 equals 7 or what minus 1, and it is easier to do it that way. But figure out what works for you. For positron, it's a little bit easier because it's all positive. So again, 11 equals 0 plus what? 11. 6 equals +1 plus what, which is 5. We'd go to the periodic table, find that number 5 is boron. Gamma emission usually comes with other things, but if it is just gamma, you sometimes will put an M here to call it metastable, but don't worry, you're not going to see that. Just know that the gamma is 0, 0, so the numbers will all be the same. A lot of times gamma comes with other stuff, so it'll say like beta and gamma emission. So you just throw the gamma in there, but it's not actually going to change any of your math because again, it's a 0, 0. So this is a little summary of all the different particles, and it shows you an example of the reactions. Why don't you try it? So pause and see what was the product when AT undergoes alpha and beta decay. We're going to do both of those. And you can do them separately if you want to, but you can also do them all at once. I'll do them separately just so you can see. Give that a try and come back. All right, so hopefully you've worked this out. Let's try it. AT210. So if I look on the periodic table, I gotta find AT, astatine. That is number 85. And so that'll be my protons. It undergoes alpha decay, which means it's going to break into an alpha particle. Alpha is 42He. I need to figure out what this is going to be. So I've got kind of 3 blanks to consider. So I'm going to say 210 equals 4 plus what? So what would go in the blank? 206. So automatically I know, well, we haven't finished yet. So we could try to look for answers already, but we haven't really finished because we have to also do beta. Beta is not going to change the mass, but we'll look at it. So bottom is 85 equals 2 plus what? That would be 83. And then just double check to make sure your math works. 206 plus 4 is 210. 83 plus 2 is 85. Remember, this is like an equal sign here. I know it's not equal, but we're pretending that just for this reaction. For 83, we're going to look to see in the periodic table who number 83 is. Number 83 is Bi, bismuth. What's in your Pepto-Bismol? So you always look to the atomic number, tells the element. All right, so now we have to also do beta decay here. So we can't be finished, and I would probably want to just check the Bi206 because I see that's what we get when we do alpha, but we gotta also do beta. So we do 206, 83 bismuth, and if it goes through decay or emit, so the word decay, or if it says emit, that means the particle is a product. If it says like capture or added on or something like that, absorb, that means the particle is a reactant. We're not really going to see that in this class. So we're only going to be really looking at emission. So we know it's a beta particle. So again, I have to memorize what a beta particle looks like. And then I have my 3 blanks. So top number is pretty easy with this one. 206 equals 0 plus what? So the answer is going to be 206. And now that I know that, I could come over here and I could say, well, I know it's not going to be this one because it's not going to be 208 as my mass number. For bottom, be careful here. 83 equals -1 plus what? If you're thinking 82, go ahead and put 82 in here and then check it for yourself. Is 82 minus 1 equal to 83? No, right? So we kind of did the wrong math here. So what minus 1 is 83? That would be 84. So just be really careful because I'm sure that answer is on here. So number 84, we look at that for the periodic table. That's PO polonium. So my answer would be PO 206. Hope that makes sense. Just give yourself some time with it and let me know if you have any questions. Last topic for this class is half-life. This can be something that seems like it's going to be really difficult, but let it do its thing. Half-life is how much time it takes for 1/2 of the sample to decay or for it to go away. So if we start with 16 grams of our sample, after 1 half-life, let's say the half-life is 14 days, half of it would be left, so 8 grams left, and the other half of it would be something totally different. It's turned into a totally, we're noticing that we're turning into totally different elements now. So let's look at the blue. We start with 16, we take half of it after the first half-life. So now we have 8. The next half-life, we take half of 8. What's half of 8? 4. The next half-life, we take half of 4. What's half of 4? 2. So if you just look at the blue, we're just decreasing by half every half-life. Now, if you want to think about it in reverse, like how much of the sulfur am I making? We start with 0, and then we're making as much sulfur. Notice that the total mass of this one and the total mass of this one is the same. So if we make 8 here, then if we are going down to 4, but we gotta equal 16, I don't think you'll see any questions where you have to figure out what this other top one is, but you can just kind of see it's not just necessarily just disappearing. It's not going away. It's just not phosphorus anymore. It's sulfur. And so half-life is just an independent property. It's an intrinsic property, so it doesn't matter how much you have, temperature, pressure, anything like that. That's just the sample, the property of that sample. So some half-lives that we can be familiar with. The carbon-14 is a really important one because we use this for archaeological dating. It takes about 5,000 years for half of carbon-14 to go away. And so we can test how much carbon-14 is in something and tell how old it is. And we use a lot of stuff for medical purposes. And so half-life, you may have looked at a half-life of a medication, right? The half-life of a medication, say in your system, half of it will stay in your system for that long. And then that means that at the end of that half-life, so for example, if you put iodine 131 into a patient, after 8 days, half of what you put in is going to be converted to something else. So how long would it take for it to be gone out of your patient's system? Well, we have to consider so 50% is after 8 days, 25% is after 16 days, and then you keep halving your percentages again and again and again and again and again. It does take a little bit longer to leave your system. Then maybe just thinking about 8 days is not, it's only halfway done from your system. So let's think about a problem here. If the half-life of iodine 131 is 8 days, how much of a 100 milligram sample remains after 32 days? So it's been 32 days since I gave the patient iodine 131. I gave them 100 milligrams. How much is left after 32 days? So we can determine how many half-lives are in that time. So if one half-life is 8 days, we use this like a conversion factor. 32 days would be 4 half-lives. So we're going to cut our sample in half 4 times. Why don't you try, pause, try it, and then come back. So if you take 100 and we cut it in half 4 times. Now, they're showing you just times by half 4 times, but I like to actually cut it in half myself and just see what this is. So we're going to cut it in half 1 time. That's going to be 50. If we're thinking about sig figs here, we would keep 3. That's 1 half-life. And I'm just going to mark this as I go. The next half-life, we're going to cut it in half 1 more time. So we got 4 half-lives to go. So there's 2 half-lives. This would be 25.0 milligrams. We'll cut it in half again. That's 3 half-lives. This is going to be 12.5 milligrams. And then we'll cut it in half 1 more time. That's 4 half-lives, and that's going to be 6.25 milligrams, which is my final answer. Or you can think about it divided by 2, divided by 2, divided by 2, divided by 2. Each time you have a half-life, you're dividing by 2, right? So divide by 2 to the 4th if you're mathematically inclined for that. I think just writing it out like this is really easy to track. Take what you're starting with and cut it in half that many times. That's how much is left over. So we use archaeological dating with half-life, with the carbon especially. And so when the organism dies, carbon-14 decays without being replenished. And so we can kind of date things from that. So why don't you give this a try? It's kind of a similar problem. And then I will tell you your answer. And then you can let me know if you have any problems. All right. Hopefully you gave it a try. So if we start 24 days, how many half-lives is that? It's 24. So 24 days. 1 half-life is 8 days. That's going to be 3 half-lives. So we're going to split 40 grams in half 3 times. 1 half-life will be 20. 2 half-lives would be 10. And 3 half-lives would be 5. So you can also think about it going in reverse, like how long has it been? And if you're like, well, if I have 5 grams and it's been 3 half-lives, I would just, figure out how much I had here or figure out how long it's been. We'll say, oh, well, if you go from 40 to 5, that's 3 times you cut it in half. That's 3 half-lives. If each half-life is 8 days, that's 24 days. So do the homework and just play around with it. Let me know if you have any questions.